3, 2, 1. Welcome back to Advent of Code 2022. This is day 9. If you guys like these videos, hit that like button. I really appreciate it. Yeah, I think we're ready to get started. Let's close these other tabs and click on day 9. Let's go. Rope bridge. The rope bridge creaks as you walk along it. You aren't sure how old it is or whether it can even support your weight. It seems to support the elves just fine, though. The bridge spans a gorge which was carved out by the massive river far below you. Beautiful. You step carefully. As you do, the rope stretches and twists. You decide to distract yourself by modeling rope physics. Maybe you can even figure out where not to step. Consider a rope with a knot on each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled towards the head. Due to a nebulous reasoning involving plank lengths, I'm not sure what that is, you should be able to model the positions of the knots on a two-dimensional grid. Then, by following a hypothetical series of motions, or puzzle input, for the head, you can determine how the tail will move. Due to the aforementioned plank lengths, the rope must be quite short, and in fact, the head and tail must always be touching, diagonally adjacent, or even overlapping. Both count as touching. So these two are touching, these two are touching. H covers T is touching. Okay, so these are all touching. If the head is ever 2 steps directly up, down, left, or right from the tail must always move 1 step in that direction so that it remains close enough. So TH to T dot H makes dot TH. And they go down. And if they're in this diagonal pattern and it moves up, then apparently the tail moves diagonally, not up. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. Okay, all right, so that's how the tail moves. So I guess the head we're gonna get head input as our input, and we're gonna have to model tail movement. You just need to work out where the tail goes as the head follows a series of motions. Assume the head and tail both start in the same position, overlapping. For example, here's our example input. Let's copy it. This series of motions moves the head right 4 steps, then up 4 steps, then left 3 steps. After each step, you need to update the position of the tail. Okay, so if the initial state is here, then you move right 4. Well, it's moving head. What is S? S is start, I guess. And then the head goes up and you just follow. Okay. All right. I don't think we're going to scroll through this. I think we got it. After simulating the rope, you count up all the positions the tail visited at least once. In this diagram, S marks the starting position, which the tail also visited. Pound marks the other positions the tail visited. Okay. So there are 13 positions the tail visited at least once. Are we counting the S? 1, 2, 3, 4, 5, 9, 11, 13. All right, so we count the start. Okay, simulate and count how many positions the rope visited. Okay, and let's grab the input. Nope, don't want to quit. I want to select all. Input. All right, so let's think about this. What are the questions I have? Well, first, how do we want to model this problem? We could create a grid, but that grid can be any size. So then we'd have to figure out how big the grid is. So actually, instead of modeling it as a grid, we just need to model the current position of the head and tail. And then when we move the head, we model its current position in as big a space as we want. So we don't need to have a grid. And we just need to keep track of the set of positions that the tail was in. We don't need to keep track of the set of positions the head is in, and we don't need to keep it in a large matrix. We can just keep a set of tuples. So we're going to create a position type, which is a tuple of int. It is the position in this 2D space. And start is going to be, which is a position, it's going to be 0, 0. Okay. And yeah, so let's parse this input. A direction is a tuple of a string and an int, or a instruction. All right, so that's one of these lines, and our input is a list of instruction. And so we just need to instruction equals dir and int of length. This needs to be a function. Line. Whoops. Dir length equals line.split on space, and return the tuple. And this is a stir, and this is an instruction, and we can do instructions. Okay, so now we've parsed the input into instructions, and now we just need to trace every place that the head goes. And so let's just create a function that can take the current state and then move through the next step. So we're gonna do def, what are we gonna call it? We're just gonna call it a step because we'll do each step. And our state is going to be a state, all right? So what is our state? It is a data class with what in it? We just need the current position of the head, the tail, and visited, which is a set of positions. Okay? And every time we step, and then we need a direction, which is a stir. Direction. So we're only moving one step in this step. We're not going to move 4 steps as an instruction would have. So R4 would actually cause 4 calls to the step function. And what we're going to return is a new state. All right. So we have a state with head, tail, and visited. So when we move the head, all right, so new head equals state.head. So how are we gonna move head? So let's make a def move function, move from position. So we'll just call it X. And direction stir, so it's a nice little helper function. So if direction is right, return x0, x1. So this is our base. So we want, if it's right, what is x0? So 0 is going to be our, we'll just call 0 our x position, and the second part our y position. So let's just say this is horizontal, comma, vertical. So when we move right, we want to move horizontally, so we'll do +1. And elif direction is left, then we do -1. And then we just copy this and do it again, and make this elif, and turn this to up, and turn this to down, and move this to +1 here and -1 here, and remove this. Okay, all right, so this should handle every case. Return X. All right, so when we move a position, we return a new position moving in that direction. All right, so we can do new head is move state.head direction. All right, so now we get a new head position. And then we have to do def is touching. We'll just do X position, Y position, and returning bool. All right, so now we need to determine if two things are touching this, specifically the head and the tail. So that is if X, so if they are next to each other, if they are within 1 or 0 in both X and Y, then they are touching, right? So if X0 minus Y0, ABS is less than or equal to 1, and ABS X1 minus Y1 is less than or equal to 1. And we can just return that, right? So if they are within one of both. So when they're, if we go all the way back to some of these examples, for example, this position where they would be within 1 on both X and Y. In this, they would be within 0 on Y, but within 1 on X. And here they would be within 0 on both. All right. And then if they're not next to each other, this would be within 0 on X, but be over 1, sorry, it would be 2 on X. And so it would fail this condition, and therefore it would return false. And they would be not touching. And then we just have to, we have to have a third helper function to determine which direction to move. Which direction to touch. So I'm not going to call this X and Y because we're using X and Y to represent the axes, and it's confusing to use them for this. So we're going to take this code and copy it over to which direction to touch. All right, so this will determine how to move, given that they're not touching, how to move and I guess, what do we want to return? We want to return a new position, and we'll call it move to touch. All right. And actually, let's combine these two functions. So if is touching A, B, return B. All right. So stationary, so A is stationary, B is not stationary. So if they're not touching, now we need to determine how to move. So let's handle the case where they're one apart on the same axis. So if A0 is equal to B0 and they're not touching, then they need to move on the direction of Y, right? So then return, okay, and then the direction is A1 minus B1. So what is that going to give us? What is A1 minus B1 going to give us? So if we're in this case, A1 is the head, so head 1. So sorry, we're talking about 1. So it's this case. So the head 1 in here would give us 2, and the tail 1 would give us 4. So because we'll call this 1, 2, 3, 4. So we would have 2 minus 4, which would give us -2. Hence why we failed the is touching, because the absolute value of -2 is greater than 1. So once we have -2, we know we need to move tail down 1. And so what we can do is just take the sign of that, but we know it's always going to be 2 because you never move more than 1 apart. So we're going to take advantage of this, and I think the best way to do it is take this as a direction, and then return B0. So we're not modifying B0. But then we're going to do, actually, what do we do? We did, yeah, and then we do B1 plus dir divided by ABS dir. Okay, so what this is going to give us is just ABS dir here is, or we'll call it dir underscore 1. And what this is it's a direction. It's either going to be positive 1 or negative 1. So we have our direction, which we know is either positive 2 or negative 2, and we divide it by its absolute value, which will give us positive 1 or negative 1. And then we add that to the B situation here, which is the tail. And we get, and then we're returning that new position. And the cool thing about this is this can be shared code. So we're just going to move this here, remove this line. All right, and then we'll call this y dir is a1 minus b1, and x dir equals 0. And mod, we'll call this a mod. And we're gonna int cast this whole thing to make sure we don't accidentally change to floats, because Python will do that underneath you. All right, so now we have this, and we're gonna do elif here, a1 equals b1, and then the x mod is gonna be this thing, 0, and int a0, b0. You know, I'm kind of wishing we did, like, we made position a data class with .x and .y, but whatever, we're good. And then we just want to do b0 plus x mod and b1 plus y mod. Cool. And then else. All right, so now we need to handle diagonal moves. So if they are not on the same axis, they have to move, for one of them, they have to move diagonally. And the question is, which way do they move? So how can we take this position and make them move diagonally? So one of the directions is going to be have a 2, and one of the directions is going to have a 1. But it actually doesn't matter which one is which, because we're always moving 1. So we really just need to do this calculation for both directions, and this should work. And you may be asking, like, why should this work? So what we are doing, sorry for all the highlighting, I don't know what's going on. So what we are doing in each of these cases is we are calculating the direction of travel regardless of the magnitude of travel, how much distance there is. So when we are in this head to tail case where we are off by 2 in the y direction and 1 in the x direction, by running this calculation where we take our distance and divide it by our absolute value, we are just going to get 1 up and 1 right. And that will get us traveling to this square, which is where we want to go. And then we just return x mod, y mod. All right, so this is actually really cool. This is done. So now we just need to run do the step function. So then we just do new tail equals move to touch state.head state.tail. And then we return, and then we do we return state of head equals new head, tail equals new tail, and visited equals visited.union new tail. So we add the new tail position to the visited list, and then we're good. All right. So for instruction in input.instruction, let's scroll up here. So we have our list of instructions, but they have magnitudes, and we need to call step for each of them. So so each of those instructions is a direction and a magnitude. and then we do 4 underscore, because we don't care about this, we'll just call I in range magnitude. We want to do something. So we'll start with initializing our state. State equals state. And we're going to do head equals 0, 0. Tail equals 0, 0. And visited equals the set of the list of 0, 0. So this is our starting state. And each time we run a step, we want to do state equals step, state, direction. And then at the end of our loop, we should have run through everything. We want to return state.visited. We actually return the length of that. If I can type, there we go, there we go. And that should work. I mean, we're doing each step, we're moving the head, then we're moving the tail, we're calculating where the tail's gone. I think that solves the problem. So I think I'm ready to do day 9, an example. Okay, input has no attribute instruction. I believe it is instructions. Name visited is not defined. I'll blow this up. I realize that you guys can't see some of my errors, so maybe you're not doing it. Name visited is not defined. This is state.visited. All right, and so we get 13, which is the right answer for the example. So let's run it on the input. And it runs for a bit and comes out with 5873. Submit. That is not the right answer. Answer is too low. All right, so what did we do wrong? All right, let's think about this. So we got the right answer for the example. So there must be a case that we are doing irregularly. So I guess let's, like anything, when we know we're doing something wrong, we need to start printing. So the best place to print is in this step. So we do, let's start with asserting that is touching new head, new tail. Like, let's just make sure we're doing it right. All right, we're getting an assertion error. So clearly we are doing something wrong with our move to touch. That is cool. Let's figure out where we're doing it wrong. All right, print, let's do state, print direction. Let's print everything. Print new head and new tail. All right. And then let's just do assert false. So we exit and let's go. All right, so the state is currently at 0, -1. And the tail is at 0, 0, which are touching. And then we have to move down. So the head moves to 0, -2, but the tail doesn't move with it. Why? So let's just import IPDB, IPDB.setTrace. All right, and now let's do move to touch 0, -2, 0, 0. Okay, move to touch responds with 0, -1. Why did new tail? Why is new tail -1? This doesn't make any sense. Hold on. Oh, I see. Ah, here we have a bug. It's right here. So we're moving to touch the old head. We need to move to touch the new head. So we did this wrong. This is all not necessary now. Now I think we're doing it right. We're going to rerun on our input. 5874. We're off by 1. Of course we're off by 1 because by doing it on the old position, we're actually moving 1 behind. Ugh, what a bug. Off by 1. We got the right answer. All right, so we had a little bug. We figured it out. Good work. Let's move to part 2. A rope snaps. Suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the rope ropes that broke are now whipping toward you as you fall through the air. The ropes are moving too quickly to grab. You only have a few seconds to choose how you arch your body to avoid being hit. Fortunately, your simulation can be extended to support longer ropes. Rather than 2 knots, you must now simulate a rope consisting of 10 knots. 1 knot is still the head of the rope, moves according to the series of motions. Each knot further down, the rope follows the knot in front of it using the same rules as before. Okay, so now we have a series of tails. We have 10 tails. Okay, so it's like snake. Cool. All right. I'm gonna skip through this. Now you need to keep track of the positions of the new tail, which is 9 in these examples. Visits. Okay. So I don't think this is. So this is a larger example too. So let's copy it. I don't think this is very hard. So since we have this step function and these move to touch functions that are very generic, like we can, we're gonna call this step part 1, or we'll just leave it. We're gonna create a new step. I don't think this is gonna be that hard. So we just need to treat each knot as the head of the tail of the knot behind it. And we just iteratively go through all the knots. And so our new state, so state 2 is now a data class. And it has knots. So we'll call knots, and it's gonna be a list of positions. And so instead of head and tail, which would have been 2, it's going to be of length 10. And then we just have visited still. Set a position. Cool. So now we just need a step 2. Well, I don't know why that happened. Step 2, state 2, direction, and that returns state 2. All right. So knots state dot knots. How do we want to start? First, we got to move the head. So new head is still there, still this. So and instead of state dot head, we want to do yeah, we'll keep head. Actually, I decided we're going to keep head as outside, and then the knots will be behind it, right? So it'll be 9 knots behind it. Head and then 9. Yep, so head and then 9. Length 9. All right, so new head is move state.head direction, and then new knots. And you can do this with functional programming, but I'm going to make it easy on myself and just make this a nice little imperative loop. I think you guys will be familiar with this. So for knot in state.knots. And we want to keep the previous new knot, but we're going to calculate that. So previous knot equals new head if len of new knots is equal to 0, else new knots -1. So this pulls the last knot that we just calculated, unless it's empty, in which case it pulls the new head, which is the previous knot. And then we do move to touch previous knot and knot, the knot we're talking about. And then new, and we're going to add that in the new knots, plus equals a little append statement here. And that gets us the new knots. And then we just have head is new head, and knots is new knots. And then the state visited is the tail, so that is new knots -1, the last knot. And then all we got to do is copy our part 1 code to part 2, and we got to change the state. So the tail here is going to be knots, and it's going to be 0, 0 for I in range 9, 9. So that's going to be 9 knots starting at 0, 0, and visited set of 0, 0, and then we just state. So this should be good. Hopefully we don't have a similar bug. So let's run it on example 2. Input got it, sorry, state 2. This is state 2. And step 2. Step 2. And knots. And another state 2, missing 2s everywhere. All right, we got 36. What is the answer for this? 36, okay. So we did the bigger example correctly. So let's run it on the input. And got 2467. Hopefully it's not off by 1. It is not. We are correct. That's good. So yeah, this is a pretty good problem. One of the advantages of writing good looking abstracted code that handles general cases, such as this move to touch function and these move functions, is that we were able to reuse them super fast for part 2. And this is starting to get into the set of problems, these more advanced, medium, hard problems, where these kind of things will give me, make me do it a little faster than the speedy early problems. So I'm pretty excited for the next few days, and yeah, hopefully I'll see you guys around. Peace.